Welcome back to the deep dive. We often get into some pretty deep theoretical physics on this show.
We certainly do.
But usually we're sort of tweaking the fringes, right? We're refining models, looking for a new particle here or there. The stack of sources you handed us this time, though, this doesn't just tweak physics. It feels like it's trying to, I don't know, re-axiomatize reality itself from the ground up.
That is a perfect way to put it. It's a monumental undertaking. We're about to dive into a theoretical framework that proposes our three dimensions: the curvature of space, even the very existence of gravity.
Things we take for granted as fundamental.
Exactly. It argues they are not fundamental starting points at all, but are instead emergent properties, that they arise from one single, much deeper principle.
And that's the part that just grabs you immediately. I mean, for centuries, you look at classical mechanics, relativity, even quantum theory, and we treat space, time, dimensionality as these fundamental, unexplainable brute facts.
And they just are.
They just are.
Yeah.
But this framework, which is centered on this concept of coherence conservation, argues that these brute facts are actually structural outcomes. They're the inevitable result of a system trying to find and maintain equilibrium.
And the author of these papers is very clear on this point. This is, first and foremost, an ontological clarification.
What does that mean exactly, for you, the listener?
It means we're changing the reason things happen, not necessarily the observation of what happens. The mathematical predictions of general relativity, for instance, they still hold. They're incredibly successful. But the conceptual foundation, the why geometry seems to act on matter, that is completely reset.
So we're looking for the underlying structural logic, the logic that selects the reality we actually inhabit.
Exactly.
So our mission today is to take these incredibly dense, really dense theoretical papers and pull out the core concepts. We need to explain how this one principle, this coherence conservation, necessitates three dimensions.
Not two, not four, three.
Right. And then how that same principle creates geometric curvature, and from there, why gravity is universal. It tries to tie all of those gigantic features together under a single umbrella.
We really need to trace the argument logically. We have to start from this maximally unconstrained, non-dimensional state, and then walk through the process of saturation and see how it builds up to the macroscopic physics we see every day.
Okay, let's unpack this. We're going to find out why three dimensions aren't just some arbitrary cosmic lottery win, but a necessary, structurally selected choice.
To really get the scale of this, we first have to ground ourselves in the context of, traditional physics. When you look at the big successful theories of the 20th century, general relativity, the Standard Model, they all begin by assuming a stage to play on.
A four-dimensional manifold. Three of space, one of time. It's the given.
It's the given. If you ask a classical physicist why there are three spatial dimensions, the honest answer is usually something like,
because that's what we see, and our equations work really well in three dimensions.
Precisely. There's no causal mechanism in those theories that explains why the universe stabilized there, or why dimensionality is a discrete integer. Why 3, not, say, 2.7? It's just an axiomatic necessity.
It's an input to the model.
It's an input. The concept of coherence conservation just flips that entirely. It makes dimensionality an output. It posits that space and dimension are emergent properties of a process called coherence saturation.
Okay, we absolutely cannot go any further until we ground that core concept. The sources define coherence as the underlying organizing principle, but it's a bit too abstract. For you at home, needing a mental model, what is coherence operationally?
And that is the essential challenge, because coherence in this model is more fundamental than energy or momentum. So think of it like this. Coherence is the capacity for stable, sustained organization.
The potential for informational complexity.
The potential for structure to persist. That's a great way to put it. The theory states that in any physical process, this capacity, this organizational potential has to be conserved. It can be transformed, it can be dispersed, or it can be condensed, but the total potential always remains constant.
Okay, so if I'm looking at a highly ordered system like a crystal lattice or a stable atom, I'm seeing highly condensed, saturated coherence.
Right.
And if I'm looking at a hot, disorganized gas, I'm seeing dispersed coherence.
Exactly. The total stuff of organizational potential is the same in both systems. It's just in a different form.
And so the process of coherent saturation is just the system's natural tendency to organize that potential into the most stable, most efficient structures it can find.
Yes. That dynamic process of seeking maximal stability is the engine that drives the emergence of all these physical features we're talking about.
So let's follow that emergence. The papers say we have to start in the unconstrained state. What does that even look like before coherence has had a chance to organize anything?
It's a conceptually radical place to start. In this unconstrained state, coherence is just dispersing freely, randomly. And in that state, there is no dimensional structure at all.
Nothing.
We're talking about a reality without a metric, without defined directions, without any notion of extension or distance. It's just pure potentiality, unorganized dispersion.
Hold on, let me stop you there. Because my brain immediately hits a wall. If there's no metric, no extension, how can we even talk about variation or dispersion? Doesn't the word dispersion imply spreading out across some kind of space?
And that's where our language, which is built on a spatial reality, forces us into a conceptual box. The variation here isn't spatial in the way we think of it. It's variation across degrees of freedom. Or maybe think of it as admissible configurations.
That's more like a statistical distribution of potential interactions.
That's a much better way to think of it. The system can vary, but that variation hasn't been projected onto a spatial canvas yet.
It's pre-geometry. The potential for organization exists, but that organization hasn't found a stable structural way to represent itself.
Exactly. Dimensionality only appears, it is literally created, when constraints enter the picture and limit that free dispersion. These constraints are the architects of space. They force the system to adopt distinct, independent modes of variation that can persist without immediately dissolving the very structure they create.
So the constraints are the rules of the game. They say, you can disperse your coherence this way, but not that way. And every successful way that remains open. That's what we call a dimension.
That is the mechanism of emergence. Dimensionality is the consequence of the search for stability. The system is dynamically trying to find the maximum possible freedom, the maximum capacity for interaction and complexity, while simultaneously obeying the fundamental law of coherence conservation.
And any successful, stable solution to that problem has to manifest as these persistent degrees of freedom. And those are our dimensions.
Yes.
It's just completely reframed space. It's not an empty box that we fill with stuff later. Space is the organized pattern of the constraints themselves.
It is the architectural outcome. We have to throw out the idea that dimensions are just directions in a pre-existing space. They aren't. They are the channels of persistence that were carved out by the constraints.
Okay, so let's dive into those channels. The definitions in the source material here are absolutely crucial to get right. We're moving from this general idea of organization to the very specific selection of D equals 3.
Right. And in this framework, for something to be called a dimension, it has to meet a much higher bar than just being a mathematical axis you can draw on paper. It's defined functionally as a stabilized channel of permissible variation. That definition is key because it emphasizes that a dimension has to be robust. It has to be able to support a sustained flow of coherence without causing a structural collapse.
A stabilized channel of permissible variation. Okay, so if I use a simple analogy, it's like a system of water pipes. The pipes are the channels that permit flow, that's the variation, but the pipes themselves have to be structurally sound stabilized, so the whole system doesn't just burst apart.
That's a great analogy. And that leads directly to the stability criterion. This is the ultimate test. A potential mode of variation only gets to count as a dimension if coherence can vary along that mode without destabilizing the entire organizational system.
So if I hypothesize some extra fourth dimension, but any fluctuation along that degree of freedom causes this ripple of instability that just destroys any localized structure,
then that potential dimension is rejected. It's vetoed by the universe's fundamental need for stability.
it fails the test.
Fails the test. If variation along a mode leads to systemic instability or collapse, that mode simply cannot persist. It means the structural cost of keeping that degree of freedom open is just too high for the conservation law to support.
So dimensions aren't arbitrary choices. They're the very few successful, structurally sound paths the system found to organize and conserve coherence efficiently.
They are non-arbitrary solutions to a structural problem.
And this criterion seems to naturally solve a huge problem that classical physics just sort of accepted as a given. Discreteness. Why are dimensions integer values? Why do we have D3 and not D2.7 or something?
The sources are really explicit about this. They state that, and I'm paraphrasing here, Partial or fractional modes of variation do not support stable dispersion. Think about structural stability again with your pipe analogy. You can't really have half of a structurally sound pipe. The system either succeeds in finding a constraint pattern that supports a fully independent, stable mode of variation, or it doesn't.
It's an all-or-nothing requirement for persistence. If a mode is only partially successful, it just leaks coherence, becomes unstable, and it collapses back into the more stable, saturated modes that do work.
It's like a structural phase transition. A mode either saturates the requirement for stability, and it counts as 1, or it fails to support that stability, and it counts as 0. Dimensionality emerges as these discrete integer values because it's just the total count of the independent, fully saturated, and persistent modes that are available to coherence.
Which brings us to the million-dollar question. Why does the system only successfully stabilize 3 of these channels? The answer given is that D3 is a stable equilibrium between dispersive freedom on one hand and structural constraint on the other. We need to spend some real time on this, detailing this balancing act.
This is really where you see the structural engineering of the universe, so to speak. The selection of 3 dimensions isn't about maximizing complexity, not in a raw sense. It's about maximizing persistent complexity.
Okay.
It's the minimum architecture you need for a universe to have long-lived structures that can actually interact with each other in meaningful ways.
Let's break that down. Let's start by looking at the failure on the low end. Fewer than 3 dimensions. Let's imagine a 2-dimensional D2 universe.
A 2D reality is just. It's overly restrictive. Now, you can have some basic organization in a D2 system, but you severely limit the capacity for complex, non-intersecting interaction paths.
Right, if you try to build anything complex, say a stable solar system or even a biological structure like a digestive tract, you run into immediate organizational bottlenecks.
Absolutely. In 2D, a line separates a plane into 2 disconnected regions. You can't have complex internal structures without cutting off circulation paths. And as you mentioned, gravitationally, orbits in 2D are often unstable. Any small perturbation sends an object spiraling into its star or flying off into space.
So coherence is so severely constrained that it lacks the dispersive freedom it needs to allow for hierarchical structure. Simple things can form, but they can't achieve the complex, layered organization you need for enduring systems.
Exactly. A D-less than 3 reality might conserve coherence, sure, but it does so at the cost of interaction and complexity. It would be essentially sterile or far too ephemeral. The structural potential is just too low.
So the system is structurally sound, but it's structurally boring. It fails the test of supporting complex, persistent organization.
Right. Now let's look at the other side of the coin, the failure on the high end. More than 3 dimensions, say D4 or D5. Here we get the exact opposite problem, excessive dispersion.
Mathematically, a 4-dimensional manifold seems perfectly fine. But ontologically, in this framework, what goes wrong?
Well, if you stabilize 4 or 5 independent channels for variation, you're allowing coherence to spread out too fast and too widely. This rapid dispersion actively undermines stability. Imagine trying to hold a structure together when there are just too many available independent pathways for its organizing energy to escape.
The structural integrity just dissolves. The degrees of freedom permit the constituent parts to escape the organization too easily. Any attempt to form a complex, stable bond like an atom or a molecule, it's immediately challenged by this rapid dispersal of coherence away from the structure.
The persistence of any structure becomes highly transient. The strength of the localized binding forces, like electromagnetism, is often just insufficient to overcome the rate of dispersion in higher dimensions.
So, for example, in D4 gravity and electromagnetism, the force laws change, right? They fall off much faster with distance.
They do, and that often results in unstable orbits or field decays that prevent any kind of long-term bonding. You can't make enduring, complex objects. The conservation of coherence is achieved through constant dissipation, not stable persistence.
So D3 systems are too chaotic. Structure might form for a fleeting moment, but it's too transient to sustain any kind of complexity over meaningful timescales.
Which leaves us with 3 dimensions. The source material argues D3 occupies this unique, perfect balance. It's the only regime where coherence can both spread disperse enough to allow for interaction and complexity, and remain bound to stabilize and allow for persistence and conservation.
It's identified as the minimal structure that allows coherence to, quote, disperse interact, and stabilize simultaneously.
And that concept of minimal structure is so powerful. It's the Goldilocks zone. It gives the universe just enough freedom to be interesting, but not so much freedom that it tears itself apart instantly.
And this structural selection, this choice, links directly back to that core mandate of coherence conservation.
It has to. D3 is stable because it's the most efficient configuration for conserving organizational potential across all scales, from the quantum level all the way up to galactic structures. Systems that try to deviate from this saturation point either achieve stability at the expense of complexity, like in D3, or they achieve some momentary complexity at the expense of persistence, like in D3.
So D3 isn't an accident. It's the inevitable, structurally selected configuration.
Yes.
Which means when we look out at our universe, we're literally viewing the architectural footprint of coherence conservation. That's a complete conceptual overhaul of what space is.
It is. It's the enduring, stable result of this fundamental balancing act.
This idea that D3 is structurally necessary, it must fundamentally change how we view those extra dimensions that are proposed in theories like string theory.
It does.
Traditionally, those theories treat them as real, albeit curled up spatial realities. What does this framework say about those mathematical artifacts?
This is a really crucial clarification the papers make. The framework rejects the interpretation that these mathematical appearances of higher dimensionality correspond to some deeper reality. It argues instead that they are representations of unresolved dispersion, or maybe incomplete stabilization.
So those extra degrees of freedom we see in the math, they aren't tiny hidden spatial directions. They're more like placeholders for the system's potential to vary that just hasn't finished condensing into stable structure yet.
That's precisely the idea. They exist in the mathematics because the system hasn't fully saturated the coherence constraints in that particular regime. In highly energetic or very localized states, or perhaps in the very, very early universe, the system might momentarily exhibit these extra degrees of freedom, but they are dynamically unstable in the long term.
So they aren't curled up and waiting for us to find them. They're actually expected to be dissolved back into the three persistent dimensions once the stabilization is complete.
That is the key distinction. As coherence condenses further, as the system cools and fully saturates, these mathematically appearing degrees of freedom are expected to collapse into the familiar, stable, three-dimensional structure. The instability that's inherent in any D3 regime ensures they just can't persist as independent spatial dimensions.
Which gives you a mechanism for dimensional reduction that's based on structural necessity, not some arbitrary process of compactification.
Right.
This also sheds some light on the universality of D3. If dimensionality is selected by this stability requirement, why is it constant across vast cosmological distances? Why is it the same here as it is in the Andromeda Galaxy?
Because dimensionality in this model isn't a local property of a particle or a field, it's a collective environmental property. Once the underlying coherence field, the foundational structure of the universe, saturates and achieves that stable D3 regime, that constraint pattern becomes globally shared.
So every system that operates within that field inherits the D3 architecture.
It has to. It's like saying, once the environment stabilizes into solid ground, every house you build on that ground is going to use the same three structural axes. It's an environmental constant, not a particle-by-particle choice.
Okay, so now that we've established why space emerges as three-dimensional, we have to move to the dynamics within that space. We have to talk about gravity.
And we have to do it while respecting the incredible empirical success of general relativity, but looking to replace its conceptual foundation.
Right, so we go back to general relativity's famous mantra, matter tells space-time how to curve, and space-time tells matter how to move. The conceptual tension there has always been that geometry, which we normally think of as a descriptive math tool, is somehow elevated to an independent physical actor. It's causing motion.
And this framework resolves that tension by saying, very simply, geometry never acts.
Geometry describes.
Geometry describes. The action is happening at a deeper level. Curvature, in this model, is completely redefined. It is not an intrinsic property of space as some kind of substance. It's not a cause of motion. It is the representational signature of a coherence gradient.
A representational signature. Okay, we need to dissect that. We have our stabilized D3 space, our architectural footprint. How do we get gradients within that footprint?
Well, remember that the emergence of geometry required coherence to stabilize under constraint. But those constraints don't have to be uniform everywhere. They can vary in their intensity.
Okay.
The non-uniform condensation of coherence, which is what we call mass energy, creates localized differences in the underlying structural rigidity of space.
Let's use an analogy, maybe like a fluid medium that has different densities or a flexible structural lattice that's tighter in some places than others.
That's a perfect way to visualize it. Imagine a region where constraints are highly concentrated. This would be due to a lot of condensed coherence, like a star or a planet. This is a high constraint area.
And in that area, there's significantly reduced dispersive freedom for any surrounding coherence.
Exactly. Now, move away from that mass into deep space. You're in a region of low constraint where variation is much more permissive.
And that difference in the local constraints, the density of the coherence organization, that is the coherence gradient.
Yes, and this non-uniformity is what our geometric language records as curvature. Geometry simply encodes how the capacity for coherent variation changes from one point to another. The sharper the gradient, the greater the difference in constraints between 2 points, the steeper the recorded curvature.
So geometry becomes the stable, three-dimensional language we use to describe the underlying state of the coherence organization. It's a map. It's a map of the constraint landscape.
Which completely demotes geometry. It's no longer the actor, it's the output. Geometry is passive. It's the organization of coherence underneath that's the active principle.
So geometry provides a stable encoding of the coherence organization's effects. It describes the constraint field. It does not act on objects or cause their motion.
Precise.
So then, if geometry isn't pushing objects around, how do they move? We need a kinetic principle, something that operates on the coherence field directly, not on the geometric map.
The central kinetic rule in this framework is that objects follow the path of least coherence cost.
I love that phrase. It sounds like an efficiency principle. How does an object calculate its coherence cost?
Well, every physical system, from a photon to a planet, is itself a localized packet of saturated coherence. To persist, to hold itself together, it has to constantly interact with the surrounding coherence field, maintaining its own internal organization against the external constraints it's moving through.
So moving through a region with a coherence gradient means it has to navigate these varying levels of constraint.
Right. And if an object tries to move against a strong constraint gradient, say climbing directly away from a high-mass object, the cost to its own internal coherence structure is high. It takes more organizational effort to maintain itself on that path.
It's harder to hold itself together.
It is. So the object naturally chooses the route that minimizes the effort required to maintain its internal stability and organizational integrity. It seeks the easiest path through the constraint field.
And when this path of least coherence cost is projected onto our stabilized geometric canvas, our space-time manifold, it appears geometrically as a geodesic.
That's the beauty of it. It preserves the mathematical success of general relativity. The geodesics are still the correct trajectories, but it completely replaces the underlying physical mechanism. The object isn't seeking the shortest path in a curved space. It's seeking the path of maximum organizational efficiency in the coherence field.
And the geometry, the curvature, it's just describing that optimal least cost route.
Yeah.
If the geometry is highly curved, that just means the coherence gradients are very steep, and the easiest path requires a big deviation from what we'd call a straight line.
Exactly.
This grounds motion entirely in something like thermodynamics or informational efficiency, rather than a mysterious geometric force. It provides the why that GR was missing. Objects move not because geometry commands them to, but because their own persistence demands efficiency.
And this reinterpretation has profound implications for gravity itself, especially when you look at its unique features compared to the other forces.
Okay, let's start with its most puzzling trait. Why is gravity universal? Why does it affect everything? A neutron, a beam of light, a chunk of antimatter, regardless of its composition or its charge or its internal structure?
The answer is baked right into the foundation of the model. Gravity's universality is a direct result of the universality of coherence conservation itself.
Okay.
The gradients are based on variations in the fundamental structural architecture of space, the constraint field. They're not based on particle-specific properties like charge.
So other forces, like electromagnetism, they depend on an object having a specific characteristic, like charge. But gravity is unavoidable because all objects are embedded in and rely upon the same underlying coherence architecture just to exist in D3 space in the first place.
Any system embedded in that stabilized regime must respond to these variations in constraint, simply because responding efficiently is the requirement for its own persistence. Every single object is equally subject to the local cost of maintaining coherence across the gradient. It's like a non-discriminating architectural tax.
This also clarifies why the geometric effects become so dominant at large scales and high mass densities. Why does GR, this geometric description, become the most important game in town when you're dealing with planets and stars and galaxies?
Because large mass densities correspond to deep coherence condensation. These are the areas where the organizing principle, coherence, is highly saturated and localized, and that leads to extremely steep, very pronounced gradients.
And when the gradients are steepest, the geometric signature, the curvature, becomes overwhelmingly pronounced. It just dominates all the other interaction effects.
Phi mass equals high structural rigidity, which translates to a sharp, clear curve on our descriptive map.
And conversely, this framework helps us understand the other end of the scale, the quantum realm. Why does curvature seem to lose its meaning in these highly dispersive or quantum regimes?
Well, because those are states where the local coherence is too fluid, too active, or too dispersive to maintain a stable projection.
So if the underlying coherence hasn't fully saturated and stabilized the D3 projection in a local area, the geometric description itself becomes invalid. The map is no longer useful.
That's the implication. General relativity fails in the quantum domain because the very stage it operates on, stable, localizable, three-dimensional geometry, is temporarily dissolving back into that state of unresolved dispersion.
So let's summarize this whole section with the framework's ultimate definition. Gravity is not a fundamental force. It's not a fundamental geometric law. It is the macroscopic expression of coherence conservation once space has emerged as a valid projection.
And, to use the author's own striking metaphor, curvature is the shadow cast by coherence gradients onto stabilized extension. It's a descriptive shadow, not the active hand of causality.
We have covered an extraordinary amount of ground here. We've gone from this abstract organizing principle, coherence conservation, all the way to deriving the very structure of our reality. 3 dimensions, universal gravity, curved spacetime. The claim is just, it's profound. We've unified the explanation for space, dimension, and gravity under one single structural principle.
And in doing so, the framework has pulled off a complete conceptual inversion. We've managed to preserve the empirical success of physics, the trajectories are right, the field equations work, while completely restructuring their foundations.
As the author states so confidently, nothing empirical has been altered. Everything ontological has been clarified.
And that really is the ultimate goal of theoretical physics, isn't it? To provide necessity where before there was only contingency.
Absolutely. So let's run the scorecard for you, the listener. Let's review the 5 fundamental questions that this framework claims to have successfully answered and tie all these concepts together one last time.
All right. First, clarification. Why space emerges? Space is not an empty canvas. It emerges as a stable, persistent projection only after the organizing principle of coherence has saturated the available constraints and defined a stable capacity for extension.
Second clarification. Why geometry works. Geometry is the perfect descriptive tool. It works so flawlessly because it is this reliable 2-step encoding system for representing the effects of the underlying coherence organization and its inevitable gradients. It's a stable map of an active territory.
Third clarification. Why dimensionality stabilizes. It stabilizes precisely at D3 because 3 is the unique structural equilibrium. It provides the minimal framework necessary to simultaneously balance dispersive freedom against structural constraint, which is what allows for complex, persistent organization to exist at all.
Fourth clarification. Why curvature governs motion. Curvature doesn't govern motion. It describes the path of maximum efficiency. Motion is actually governed by the underlying requirement of persistent systems. Follow the path of least coherence cost. And that minimum cost path is what is geometrically represented as a geodesic.
And finally, the fifth clarification. Why gravity is universal. Gravity is universal because it's an expression of the fundamental stability architecture of reality. Since coherence conservation is universal and all systems must rely on that stability to persist, all systems must respond equally to the local variations in that constraint.
The structural selection argument is just incredibly robust. It shifts our entire understanding of reality from a set of, arbitrary granted features to a necessary structurally selected outcome of organizational physics. It makes the universe look less like a happy accident and more like a piece of optimized engineering.
That might be the greatest achievement here, placing the very existence of space and gravity on a foundation of necessity, not just contingency.
So the core shift here, the final takeaway for you, the listener, is realizing that the three-dimensional structure we inhabit isn't some arbitrary choice. It's the inevitable, most efficient structural configuration that's required by the conservation of organizational potential.
The architecture of reality is dictated by the need to maintain coherence efficiently and persistently over time. It grounds physics in structural necessity rather than just observational law.
It really changes the way you look at fundamental constants, doesn't it? They might not be constants we just happen to measure, but parameters that define the optimal state of coherent saturation.
That's a fascinating thought.
So let's end with a final provocative thought for you to take away, something that builds on this idea of incomplete stabilization. We established that mathematically appearing higher dimensions in this model are interpreted as unresolved dispersion degrees of freedom that are expected to collapse into D3 once saturation is complete.
And if that structural collapse is a kind of phase transition driven by the universe cooling or condensing towards its state of maximal stability, what might that imply about the actual physics of the earliest moments of the universe?
Right. Before full saturation, the universe would have been operating in a state of high dispersion, supporting multiple non-persistent modes of variation. So the question is, did the forces of physics, or even the constants of physics, appear different back then, when the dimensional structure itself was still in flux?
Were the laws of physics themselves also emergent features that only stabilized after the D3 architecture was fully selected and locked in?
The emergence of space may have been the ultimate physical phase transition, the moment that maximal potential freedom was constrained into minimal persistent structure.
And understanding that initial phase transition, where n dimensions collapse to 3, could be the key to understanding all the initial conditions of the cosmos.
Something to keep turning over in your mind as you consider the architectural footprint of coherence. Thank you for joining us on this deep dive.